Welcome back. We're going to talk about Newton's laws of motion today. There's three of them. And Newton's first law, law of inertia. Newton's second law, net force equals ma. And then Newton's third law, called law of paired forces. So this will kind of be more of just a narration type video. A couple pictures for you. For the most part, you should jot these definitions and terms and thought processes down in your notes, and I'll kind of guide us through it. So, Newton set forth three laws of classical mechanics that relates how forces cause movement, or I should say acceleration, of relatively large and slow objects. So what's a relatively large object? A relatively large object is something bigger than a molecule. We're not talking about intermolecular forces, we're not talking about electrons or protons. That kind of breaks away from classical mechanics and goes into quantum mechanics. And that's kind of the dividing line here between where Newton's laws work and then where you need to apply some quantum mechanics. We also talk about things that are going slower than 1% the speed of light. Okay, we say non-relativistic speeds. Now that's not to say that it can't go very fast. Things like a bullet or a rocket are not relativistic. They may break the sound barrier, but they're still in classical mechanics. Newton's first law has a couple tenets. It says, inertia is an object's ability to resist acceleration. So write that down. Objects with more mass have more inertia. Okay, and we can look at that. If I have a box, say this box is 10 kilograms, and then I have another box, 100 kilograms. If I apply Newton's second law, and I want to know the acceleration of these boxes from the center of mass, I can relate acceleration as the net force divided by the mass. If I increase the mass, it's going to be harder to accelerate. So I'm going to push with the same force, right? I'm going to push as hard as I can. I'm going to push that 10 kilogram box as hard as I can, and I'm going to cause an acceleration. When the box gets bigger, I'm still going to push as hard as I can. It's not like I turned into Superman overnight, although some of you may think that. I'm pushing that box as hard as I can, but the mass has increased, and so it's harder for me to accelerate, and it's just not going to accelerate as fast. It has more resistance to my efforts to accelerate it. And that's really what the law of inertia is saying. Newton's first law was saying things that have more mass are harder to accelerate, meaning they tend to do what they were doing better. So an object at rest will remain at rest better if it has more inertia, like this 100 kilogram box. An object in motion, so let's say I get this 100 kilogram box going down a hill. Let's say I get this 10 kilogram box going down a hill. Which one's going to be harder to stop? This object has more mass, has more inertia, it has more resistance to changing its movement, right? So it's going down the hill, and I got to stop it. It's going to take more force to stop it, okay? So that's Newton's first law. There's two ways that you'll typically see this. Rocket's going along, and it's got these little boosters on the side, right? So continuous force rocket thrusters. So it's cruising along. If it shuts off its engine, it's going to continue on forever, ever. But it's got these little thrusters on the side for changing direction. And so it's going to apply that thruster. Now the law of inertia says that the rocket will continue to move forward, but we've added the rocket thrusters perpendicular to that motion. And so it will now be this direction. The rockets are still burning, right? Law of inertia says that that rocket will continue on in this direction, but because those rocket thrusters are still burning, so this would be like 1 second, here's another second, we now are going this way, and the rockets are still burning, and so law of inertia says that the rocket will continue on, and the rocket's thrusters will be changing its direction, and then finally the rocket shut off, and then the law of inertia says that it would continue on and on and on. Okay, so what we get here is a turning effect from a constant external force, right? So constantly applied, the law of inertia says the rocket wants to continue on, so that value, that vector of velocity still exists because of the law of inertia, and then I've added another vector from this new force that's pushing it perpendicular. Well, new direction, law of inertia says it's going to continue on. And so essentially, if I were to take a blinky car, we'll do this in class, if I take a car and tie a string to a center post, and I set that blinky car moving, I turn it on, its wheels are cranking, and that blinky car wants to go this way, but I've got a string tied to a center pole. Well, that blinky car is going to go around in a perfect circle. However, the wheels are trying to get that thing to go in a tangential velocity, but it's got a continuous center-seeking force towards the middle here that's causing it to accelerate, not in speed, but accelerate in direction. So it's changing its velocity as it goes around the circle. That's a continuous force, okay? As soon as I cut that force or turn off that rocket, it will continue in whatever direction it was pointed in because of the law of inertia. That object wants to keep doing what it was doing unless an external force acts upon it, okay? If we talk about instantaneous force, it's a little bit quicker. It's just a one-time event. I have that same rocket burning through space at some velocity, and an asteroid comes along and hits it. Impact. Right? The asteroid goes off into space. It's no longer part of the problem here. Because the velocity of the rocket was not zero, it had some motion. It means it has some inertia. The mass of that rocket, right, wants to keep moving in that straight line, but we had an added vector of the, if I get the angle right, of the asteroid, that same angle here. I have a new vector, but that new vector is just a one-time event, okay? So an instantaneous external force or a one-time shot here is just it's a collision, and we'll talk about collisions later on. Okay, Newton's second law we've already talked quite a bit about. That is very simply the net force is equal to the mass in acceleration. If a net force is exerted on an object, the object accelerates in the direction of the force. The net external force is equal to the product of the object's mass and acceleration. Parallel forces accelerate. Anti-parallel forces slow down. So we had parallel forces accelerate. Anti-parallel forces slow down. Or we should say, in terms of acceleration, decelerate. And perpendicular forces change direction. Newton's third law is the law of paired forces. And this one's a little bit tricky, but we see it all the time, everywhere. Okay? Now, Newton's third law of paired forces says if an object A exerts a force on object B, then object B exerts a force on object A that has the same magnitude and is in the opposite direction. So equal and opposite forces, you've probably heard this. So mathematically we say force of object A on B is equal to negative force on object B on object A. Okay? What's that mean? What's that look like? Alright, so I have a box on a table, or a book on a table. the force of gravity is the earth pulling on the book. So F of G is earth pulling down on the book. Well, according to this rule, that also means that there is a paired force of the book pulling up on the earth. Right? So I have the same term, what I'm doing, my action. I have the opposite direction, and I have changed my objects. Okay, these are paired forces. Now we have many other forces acting on this book on a table as well, right? The table's normal force, and you ask, well, why isn't the book pushing down with the same amount as the table pushing up? It's like, well, it is. Okay. Now the question becomes a material science type question. Why, when I put a book, maybe it's a really, really heavy book, or maybe a rock, right, or a, I don't know, a big piece of metal on a glass table, the table is pushing on the rock, and the rock is pushing on the table with the exact same force. Why did the table break? Well, the table was not able to hold that rock. The material just wasn't strong enough, right? And so they were exerting the same force. It's just the rock was more able to deal with it. It's like if you hit a rock with a hammer, okay, the rock hits the hammer just as hard as the hammer hit the rock, and usually nothing happens. But if you get like a piece of chalk and you take a hammer and you hit that piece of chalk, the piece of chalk hit the hammer with the same force that the hammer hit the chalk, except the chalk is much more brittle and it can't handle it, and you smash it, right? So paired forces exist, and they're always equal, they're always opposite, but you might see different results because of that material's ability to withstand that force. This is equal and opposite forces, Newton's third law. This is the reason sports equipment behaves the way it does. If I want to make a better bat, right, I want to look at the reaction of these paired forces between the ball on the bat and the bat on the ball, right? Why can I hit a 90-mile-an-hour fastball farther than a 50-mile-an-hour fastball? Well, it just plain old, the ball is coming at the bat harder. The ball is going to hit the bat harder. Therefore, the bat can hit the ball farther, right? There's more energy there. Golf clubs, tennis rackets, any of these types of hitting sports, if you want to talk about running, how do you run faster? Hit the ground harder. If you hit the ground harder, the ground will push you harder and you'll run faster. If I want to swim faster, what do? Well, you pull harder, right? You exert more force from your hand to the water, and the water will push your hand faster, or you'll have more force there, okay? Usually means that you're going to go faster. So a lot of cool sports analogies in this, the third force here of equal opposite forces. Keep in mind that the force of A on B is equal to the negative force, not changing the value, but the direction of B on A, okay? And there's a very specific way to write this where we're changing the directions but keeping the verbs, switching the objects, okay? So that's Newton's third force, and that wraps up Newton's laws of motions. So the first law, second law, and third law. More conceptual type questions you'll have on these types of things. Okay? Thanks.